Okay, all Chromebooks must be completely closed for this amazing knowledge I will impart. You don't want to miss this. Okay, so let's, who knows, who can tell me what the definition of momentum is?
Are we going into our new chapter or something?
Kind of.
Okay.
Yeah. Yeah, so momentum.
It's kind of like sustained movement.
Okay, like, you can tell me what has more momentum if a truck and a car are driving down the road at the same speed, which has more momentum? The truck, okay? If let's say that you might have a hard time with this one though. What has more momentum, a car traveling at 100 miles per hour or a truck traveling at 15 miles per hour?
Probably the car. It depends on how much the
Depends,
truck
right?
is.
So is it
That could-
was it amount of
Okay, so that, but
Probably
conceivably,
the car.
that one might be tough, right? Okay, how come?
Because
it has more
speed is exponentially increases momentum.
It does not, but just see if we could, let's not worry about how they vary, but what are the factors that would impact momentum? Speed is one of them, and mass. Okay, and so when the car and the truck are traveling at the same speed, then the truck has, for sure, more momentum because it has more mass, right? But when you vary both of those things at the same time, it's hard to tell, right? The truck has more mass, but if the car has a lot more speed, then who knows? We'd have to do a calculation to find out. So what do you think the equation is for momentum? Well, momentum, we denote with a lowercase p. It's a vector quantity. What do you think it is? Mass times velocity, that's it. Yep, it's lowercase p. That's the variable we always use for momentum. Not sure why, but it's what we do. Okay, so that's momentum. Now I want to go back and revisit. I told you a little white lie earlier in the year. It's not a bad one, but I have to confess, it is a little bit of a white lie. I told you, what did we say that Newton's second law was? Third law was the action reaction. First one was law of inertia.
Oh, yeah.
Okay, what's the second one? That's the one we use 99% of the time. Oh, come on now.
Maybe it's Jeremy.
Newton's second law. What's Newton's second law? F
Equals mass times acceleration.
F equals ma. There you go. Okay, so net force equals mass times acceleration, right? Okay, that is not strictly speaking a true statement. Okay, here's why. It turns out that force is, the actual definition of force is that force is the rate of change of momentum. That's truly, if we're going to look at this in a calculus sense, that's how we define force.
It says it is the derivative of momentum.
Force
Yep.
is the derivative of momentum.
That's it. That's the true meaning of force. It's the rate of change of momentum. So it's dp dt. Now, if we're going to do this without calculus, if we're going to assume constant forces, we could just call that delta p
More, that's what I was
over delta t if we want, right? Okay. So if p equals m times v, what's that look like then? So let's do a little calculus here, right? If you're not in calculus, that's fine. This is still, the conclusion is what's really important here. So if we have force equals the derivative with respect to time of p, okay, how would we do that calculus?
And the derivative of m times v plus the derivative of v times n.
Okay, so we'd have to use the product rule, wouldn't we? Right? We'd have to say this is equal to dm dt, right? Times v plus m times dv buy that?
Yes.
Okay. But what's dm dt? The rate of change of mass with respect to time.
Non-existent?
Non-existent meaning
It
so
doesn't change.
zero, right? So the suggestion is then, did we even really need to use the product rule here?
No.
No, because we're saying that m is a constant, right? So if we assume m is a constant, then this derivative would go to zero, and we would just end up with m dv dt. Well, what's dv dt? Yeah, what is that though? What kinematic quantity is that?
Acceleration.
Acceleration, sure, so that seems to work fine, doesn't it? So that wasn't much of a lie. Shoot, that seems all right, doesn't it? 6 of one, half a dozen the other, that's no big deal, right? Except that this is not actually zero. That's the thing. It's not actually zero. dm dt is a quantity that is typically very close to zero, but it's not zero, okay? What's that? How does the mass change?
Yeah.
It just does. That's one of the things that Einstein showed us, is that an object's mass is a relativistic quantity that changes with velocity. Okay, so if we measure, and this is really bizarre, and this is where physics gets, I mean, you might want to grab your head so it doesn't spin around 360 degrees on your neck here, because it just might when you hear this, but if I was to take an object and throw it fast, I mean really fast, by us in the room, close to the speed of light, that object, I'd have to push really hard on that object to make it do that, because I got to accelerate it pretty fast, but extra fast, because from our perspective in this room, because that object has all that speed relative to us, its mass would increase dramatically. Okay, it really would. Now, does that mean that the object's mass would increase if we were driving by it in a rocket ship, traveling the same speed as the mass as it was flying through the air? Not at all. We could reach out and just grab it. It'd be fine. Because from our perspective, it would have zero velocity. But the thing is, then, everything in the room that we're flying by, all of it, everything in here, the mass would increase, right? Which is really strange if you think about this. Yep.
It's like inertia. It's like
Kind of. I mean, it kind of is. It's sort of. It's really hard to talk around this, especially when you're talking about velocities instead of accelerations. It gets a lot easier to talk about this stuff if you use the law of general relativity to talk about accelerations instead. But we don't want to probably go there right yet. So we'll just take special relativity, which was Einstein's first theory, which only refers to constant velocities, but high velocities. If the velocities are close to the speed of light, then strange things happen. 3 strange things happen for objects that move close to the speed of light in your reference frame. If they're moving relative to you close to the speed of light. Their clocks run slow, moving clocks run slow, and we've already talked about that. And that's like if you held out a big clock as you're screaming by us at close to the speed of light, and we were able to film this thing in really high-res photography, and then we could slow it down so we knew what the rate at which the clock should be progressing is, we'd find that that's not accurate at all. It's actually moving much more slowly than we would have anticipated. You wouldn't even see the clock move. It would be going so slowly. It was very close to the speed of light. So moving clocks do run slow, very true. The length of the spaceship would be dramatically compressed. So along the direction of travel, it's called Lorentz contraction. The spaceship would literally compress, and it really would do this. It would compress and it would rotate a little bit as it went by you. And the other thing that would happen is the mass would increase. And all 3 of these things have been proven with spectacular accuracy. They all happen. They really do happen. It seems very foreign to you because never in your life do you ever, or will you ever, experience any object with mass traveling close, even remotely close to the speed of light. What's really fast for us, and like a bullet's pretty fast, you can't see a bullet, but a bullet is so ploddingly slow compared to the speed of light. It's And we can calculate what it is. Well, let's do it. See what percentage the speed of light. If a fast bullet, I mean a really fast bullet, would be about, let's say a kilometer a second would be extremely fast, extremely fast. Okay, so 1 kilometer per second, that would be 10 to the 3 meters per second, right? 10 to the 3 meters per second. What's the speed of light?
3 times 10 to the 8th approximate.
3 times 10 to the 8th meters per second. So 3 times 10 to the 8th. So let's do 10 to the 3 divided by 3 times 10 to the 8th. Somebody just throw that in your calculator real quick. What is that? 10 to the 3 divided by 3 times 10 to the 8th. Okay, got an answer? Okay, times 100. Times 100. And what's that answer?
3.3 times 10 to the negative.
3.3 times 10 to the negative what? 4. So it'd be about, a bullet is about that percentage of the speed of light. Pretty slow, right? Pretty slow. So
Well, that is super slow.
nothing, I mean, slightly different than that, but not much, right? So there's nothing you'll ever experience that's ever going to be remotely close to the speed of light. And the thing is, you got to get fairly close to the speed of light. I'll show you the gamma function up here. I'll actually do a little graph of the gamma function so you can see that the function that determines how much relativistic effects occur is nonlinear itself, and it doesn't really pick up speed, so to speak, until you get pretty close to the speed of light. It's pretty tame until you get close to the speed of light, and then things start to happen fairly dramatically. So you'll never see it. I mean, you'll never see any, this stuff is so bizarre to you because it's completely outside of your possible realm of experience, right? But it really does happen. So when we go back to this, equation, if you want to treat physics more accurately, you really can't use the version of Newton's second law that I gave you previously. My little white lie is great. It's easy to use. And anything that we've ever done in this room is completely unaffected to any degree of precision or accuracy that we would ever use in even the best of labs. This is fine, right? It's never going to be an issue until you start to get things that are traveling really fast. Right? So, but ultimately, if you want to deal with all physics and not just everyday classical physics, the real definition of Newton's second law is that force is equal to the rate of changing momentum, dp dt. And this term doesn't go away. It's there. And what I want to do, and I just kind of thought of this before class, and I haven't done it yet, but I got to think of a way to demonstrate this to you, is I want to show you graphically how much of a contribution each of these two terms makes to what percentage of the force they're eating up as you apply force to an object. Okay, and that's going to depend on the speed of the object, but as a function of speed, at any earthly speeds, essentially how much of the applied force is being consumed by this term. Does that make sense what I'm saying? How much of it would be manifest in calculations we could make using F equals ma? I mean, all of it essentially, right? There's very little that would ever manifest itself in this term, okay? But I want to show you that eventually that flips. And you get to a point when you're dealing with relativistic physics, which people would do if they were talking about particle accelerators, or if you're talking about studying cosmology or something like that, where you're looking at velocities that are close to the speed of light. Then this term can dwarf this term, right? Eventually, if you push hard enough on something, like take an electron at the Stanford Linear Accelerator Center, you get them close to 99.999999997% speed of light. Very fast, right? So you're putting all this energy into this little packet of electrons, this tiny little packet of, you can almost count the electrons, it's such a small number. And you're pulsing the klystrons, these superconducting klystrons in slack, and at the moment that you do that, for the microsecond it takes to, to charge the thing up and discharge it and pull the charged particles down the 3-mile long tube, you're using as much power as the rest of the Bay Area combined, and you're investing it in that one little packet of electrons. Well, they go pretty fast, right? But why don't you just double the power and make them go twice as fast then, right? If you need to go a little faster. What's the problem with that? When you're getting that close to the speed of light, when you're getting that close to the speed of light, so you're getting within, I don't know what that works out to be, but say 100 millionth of a percent of the speed of light.
The equation changes.
The equation changes, right? Then you start to see that this term right here is the term that becomes important, and this one is nothing, right? So all of that extra energy you're investing, all of that force that you're applying through the magnetic field to the particles ends up going to changing their mass, and very little ends up actually changing their velocity. You get that? So you sort of start to push up, these things start to get so heavy. Heavy's a bad word, but their relativistic mass starts to increase, and so you can push harder and harder and harder, but the more you push on them, the more their mass increases, which further, that's foiling your attempts to make them go faster, because now they've even got more mass to push, right? And so things change, right? So there is a realm of physics where this white lie is more than a white lie. It's a pretty bad lie, right? Because when you get into that realm, this is the term that ends up being really important, okay? So here's the gamma factor, and I don't typically show this to physics classes, but this is it. So if you wanted to calculate like relativistic mass as a function of speed, here's what it would look like. Relativistic mass as a function of speed would look like rest mass. What do you think that is?
Just what we normally use as mass?
Yeah, our normal mass that we'd measure at rest, right? When it's not moving at all, divided by what we call the gamma factor, which is 1 minus v squared over c squared, and what's c? Speed of light. Yeah, so if we were to graph this thing, here's what it looks like. Okay, so let's set this up so you can see there's 0, right? We're gonna say that the rest mass, to give it a number, the rest mass is 1 kilogram. Okay. Now so what we're graphing here is mass as a function of velocity. Okay, and all I've done is that's just the gamma function we just graphed, right? Where x is equal to v, the rest mass is 1 kilogram, and there's my c, 3.0 times 10 to the 8th, right? So what you notice is that for slow speeds, this thing doesn't change at all, and these aren't very slow speeds. Like if I go to that point right there, that's the point when your speed is 2 times 10 to the 7 meters per second. So that's pretty fast, right? 2 times 10 to the 7 is 20 million meters per second. Okay, so that's a lot. That's a whole lot, right? That's what the circumference of the Earth would be. Circumference of the Earth would be, somebody do this real quick. What's 6 times 10 to the 6 times 2 pi r, times 2 pi.
3 million.
Probably 30 million.
37,600,000.
Okay, so so here we are at about 37 million, right about there, something like right there maybe. That's close enough, right there. So that's making 1 circumference around the Earth every second. That's pretty fast, right? At that speed right there. At that speed right there, your 1 kilogram mass would have a mass of 1.0076 kilograms. So you've added an additional 7.6 grams of relativistic mass to that thing, even pushing it that fast, which is so much faster than any earthly device we've ever even conceived of building, right? So the effects are small, okay? But let's look at this as we move a little further out and we get closer to the speed of light.
So can photons go faster
Okay, yeah, so we'll get to that. So that's the other thing that's kind of, okay, so look what happens though when we get to, let's add one more graph to this. Let's graph x equals 3 times 10 to the 8th. So there's the asymptote corresponding to the speed of light, right? So as we get pushed closer and closer to that, what starts to happen to the mass? Gets significantly bigger, right? And if we zoom, like when we get out to, let's go 90% the speed of light. So let's go out to,
How can the mass get infinitely big? Like, I know we can't make anything go that fast.
well, it can't. It can't, and that's, okay, so let me ask you a question. Why is it that nothing with mass can go the speed of light? Exactly, because nothing can have an infinitely big mass. And so you see what we're saying? So, say it again.
Except for light.
Well, no, but light, then we'll get to light. Light is bizarre. Light
Dimensional.
light does some weird stuff. Light does some really weird stuff. So if we go out to about, let's do one more function here. Let's do x equals 90% the speed of light. So 0.9 times 3 times 10 to the 8th. And let's look at that intersection right there. So when you're going 90% the speed of light, what does your 1 kilogram mass, what's its relativistic mass?
2.2.
Yeah, 2.29, about 2.3. Big deal. So it's gained 1.3 kilograms. That's not very much. But as you get closer, now let's go out and let's go 99% the speed of light. Yes, ma'am.
Would that mean it had doubled? So if it were like 2 kilograms, or like tripled, let's just say tripled for convenience sake. So if it had been like 2 kilograms, it would be like 6 kilograms?
Yeah, so you're going to multiply it by that ratio, by 2.3, yeah.
Do black holes move?
Do black holes move? That's a tricky question, because what does it mean to move? I mean, you can, and I don't mean to be a jerk and to say, but what does it mean to move? Is movement through space, or is movement through time, or is movement through, I mean, what does it mean? You know, I mean it's movement, it's through space-time, but is it movement through space-time relative to time? Is it real? I mean, movement gets really difficult to explain.
We're talking
From-
about, like, something can't get infinitely massive, but it's like running a pretty, you just have to try.
Right, so a black hole, the short, easy answer is a black hole is going to have the same momentum it has before it collapses. So if it were at the center of a galaxy and the galaxy is moving, then the black hole is moving just like it was before, because its mass is, you understand? But it starts to get difficult when you start to get closer to a black hole, because then time is dramatically affected, and so movement starts to get difficult to describe.
So if you got a mass, theoretically, of course, moving at the speed of light, or as close as this theoretical machine could get it,
Mhm.
would it turn into like a neutron star or a black hole?
No, it wouldn't. It wouldn't. No.
Because relative to itself, it would still be.
Collapse on itself.
No, it's a good question, but no, it wouldn't. That's a very good question, but no, it's because the relativistic mass acts differently than rest mass does. Because how could you, here's the paradox you'd have to overcome for that to be the case. How could you have a black hole at certain speeds but not have a black hole at other speeds? That can't happen, right? Because there's no preferred reference frame in physics. All the reference frames should be treated equally. There should be a way to reconcile any differences in these reference frames. And so that's one way of proving that relativistic mass acts a little differently than rest mass does. Okay. So what if we do this then? If I go 0.99, okay, now it's way up there, so I'm going to have to change my scale pretty massively. So let's let the y-axis go, instead of going up to 2.7, let's let it go up to 1 million. Okay, and in that case, the intersection's way down there, right? So it's only up to 7.089 kilograms. But if we go 0.999, whoops, where is that thing? It's getting harder to see. There it is, right? 22. What if we make the string of 9s go out to the 10th decimal place?
Big
1,
number.
2, 3, 4.
Okay, now it starts to get pretty big, right? Now we're getting, now we're getting somewhere, right? I mean, it starts to climb. And you'd see that, I mean, eventually it's just gonna keep going up and up and up, but at what point is it gonna be impossible to achieve that velocity because the energies it takes are so vast, right? And so you can see what's going on here. It eventually, like, you can take any particle with mass cannot travel the speed of light because of that relativistic mass increase. And that's why, you know, people, they talk about objects moving faster than the speed of light. And they talk about, like, when you might have read this, where they've had packets of particles where they've been able to send supposedly a signal faster than the speed of light by just manipulating where particles are relative to the center of mass of the distribution. Okay, that's a bunch of garbage. You can't do that. It's just kind of like trying to use semantics to prove a point when it's, I don't know, it's a bad analogy, but you simply can't do that. You can't ever transmit information faster than the speed of light with any particle that has mass, because no particle that has mass could ever go the speed of light. So what about light itself? How can light go the speed of light?
It doesn't have mass.
It doesn't have mass. Okay. Doesn't have mass, and yet, does anybody have like a good flash attachment to a camera? Anybody a photography buff in here? I used to have one, but it's not working anymore. If you can get one, bring it, because I want to do a demonstration for you in class. It's pretty cool, and I can demonstrate that photons have momentum. It's not that hard to do. I mean, you literally could build a solar sail that would propel, if it was big enough, if it was several, you know, say tens of thousands of square kilometers in size, and you were anywhere near a star, you could use the light pressure. You could literally use the photon pressure to propel yourself at really high accelerations away from the star. And that's actually a proposal. What's that?
Count Dooku's ship in Star Wars does that exact thing, and it's called the Solar Sail.
There you go.
Well,
Yeah.
And it's a huge record. I also saw an experiment a little while ago that some university did where they had a mass on a track. And
Laser
they
beam?
pushed it with a laser.
Yeah, you could. That's one suggested possible way to put objects into orbit, is to shoot them up in the air with a laser and have a reflective disc, and you could push them. It's
Would it have
been,
been reflected?
it would,
And then reflect it back.
yeah,
Then you'd have it.
Then that becomes a
it
little
would.
saber.
You wouldn't want to be standing underneath it probably, but there's some real problems with that. But I mean, real scientists thought, wow, this sounds like this might be a good idea. I mean, you could do it. So clearly, photons have momentum. You can accelerate a spaceship with a solar sail, and you really could. That's not just science fiction. That would work. But how can that happen if light doesn't have any mass? That's a paradox of all paradoxes. How can that work? That's one of the really bizarre things about light. How can you have momentum with no mass? And it has to do with the relativistic momentum. It's because it has no rest mass, but it's traveling the speed of light, and so all bets are off. You remember in calculus when earlier in the year when we were doing limits and we had to resolve indeterminate forms, right? Indeterminate forms, in our case it was always the form 0 over 0, right? Later on in calculus, you'll look at some other indeterminate forms, for example, infinity divided by infinity, or 0 times infinity. These are all in the limit. If you get that kind of a product or a quotient, you don't know what's going on. It could be anything. It could be that there is no limit. It could be infinite, or it could be finite. And we saw both kinds, right? We saw both types of that occurring in calculus with 0 over 0. So essentially, that's what's going on in a situation like I described, right? There's some indeterminacy there, and you've got this particle, this massless particle traveling at the speed of light. Well, how can you do calculations using a gamma function, which depends on the ratio of velocity to the speed of light? Everything falls apart. And so it turns out that the physics gods just shook hands and decided, okay, this is going to be the momentum of a photon of this energy, and it really does have momentum. It's really bizarre.
Is it very significant?
It does depend on the wavelength of the light, and there are some things that do affect what the momentum of a photon is, but it's significant enough that when I do this demonstration, you can try this at home too, if you get a piece of tin foil and you get a real powerful flash attachment that's on a strobe that fires a really short duration pulse of light, you can hear the tin foil crinkle when you flash the flash attachment. It really does. It pushes against it enough that it makes it actually, you can hear the crinkling sound. So there's your proof right there. It actually does impact the tin foil. All it is a little flash attachment. So, you really can't do it. Yep.
So two things.
Mhm.
When a nuclear bomb goes off,
Mm-hmm.
can't you see with a digital camera, doesn't it make these refractions in the camera? And so in the shot you can see little red dots appearing everywhere that look like sparks around the camera kind of, and you can pick it up with a digital sensor. Because I was watching videos of bombs going off in the Middle East, and how people are speculating that they're actually really tiny nuclear bombs, because you can see this weird effect on the camera. I wonder if you heard about that. And then second of all, with that, there's this theory, it's kind of like the opposite of Dyson sphere, that the only way for life to survive after all stars have burnt out is a reverse Dyson sphere, which is where you put a giant spherical mirror around a black hole with one opening, and you shoot light in, and the black hole will accelerate the light and actually add energy to it as it goes, because there's this middle part of the black hole that's not at the event horizon, but it's not far out,
Mm-hmm.
and it somehow adds energy to anything that passes through it,
Okay.
kind of like a whirlpool.
Okay, all right, so you guys know what a Dyson sphere is? I mentioned this. Remember there was speculation that we had seen, I told you about this earlier this year, right? The Dyson sphere. Yeah, there was kind of like a ring world. Yeah, Dyson sphere, if you look at, I don't remember all the details, but if you categorize, you probably know more about this than I do. If you categorize civilizations based on their level of engineering, have you guys read this before? So you can do a level 0, 1, 2, 3, and if you do, at some point you start to get into high enough levels that we're not there. But I can't remember what the hierarchical type is, but when you start to be able to make impact on a planetary scale, which we're arguably getting to, that's a certain level. Then the next level is, can you impact things on a solar scale? So could you, for example, build a Dyson sphere around a star, which would be just a massive array of, say, solar collectors that would harness the energy being emitted by the star, and then you could turn that into, you have this tremendous source of energy for engineering on a huge scale, right? And so obviously we're a long ways away from that. We don't know if there have been any civilizations that could do that, but if you speculate about kind of the length of time we've been on Earth and average until, blah, 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 you start to think, well, okay, that's reasonable that there could be civilizations, probably mathematically, statistically, probably are in our galaxy that do this kind of thing. And so there was earlier this year, there was a star whose brightness started to wane on a really short scale, like a 10-year scale, which we'd never seen before. And people started to speculate that, is this a Dyson sphere? Have we encountered some civilization that's so far beyond our level of advancement that we got to be worried about this? And it turns out it was explained by some dust clouds, and it wasn't that. But people were a little concerned for a while. There's some scientists started to look at that and say, wow, that's strange. That was a plausible outcome. Yeah.
So this is only loosely based on it, but in Star Wars 7, when they suck the power of the sun into the planet and then shoot the laser out, how plausible?
Not very plausible. And what Nick was saying is not plausible either, because when you get around a black hole, I thought I maybe mentioned this, but when you get around a black hole, you start to curve space so massively that when you get about, you know what the event horizon is, right? The Schwarzschild radius. That's the part of the sphere that you would see from a distance. If you looked at the Schwarzschild radius and you were to say, okay, it looks like it's about yay big, the radius would be what you would anticipate seeing there. In reality, if you actually entered a black hole, the center would be a lot further away than you think, because space would have been so massively distorted.
Could you encompass a black hole?
Well, and that's the next level, would be after a star, then it would be a black hole. Can you engineer around a black hole? But the problem is with this, when you get down to three halves times the event horizon that you see from a distance, so 1.5 times the event horizon, the curvature of space is so severe that it flattens out the universe into a plane. And so you would no longer, this would look really strange, but you would see the spherical object, you would see it start to unfold as an infinite black plane, and then all of the universe. You could see things on the backside of the black hole if there were such a thing. Somebody was standing there waving exactly on the other side. You would see them in a ring waving, it'd be distorted in a ring, and you would see all the way around to the backside of the black hole. There's nothing that you couldn't see there, and every star that was behind the black hole or even in that part of the universe would all be mapped over to this one hemisphere of your three-dimensional universe at that point. And what that means, though, is centrifugal force and centripetal force would all be backwards. The quote-unquote centrifugal acceleration that would prevent you from falling into the black hole. Like if we orbit the sun, all you got to do is go pretty fast, tangentially, and your speed will prevent you from falling into the sun, right? Our planet does that. That's why it doesn't fall into the sun, because it's got enough tangential speed to fall around in a circle, right? You can do that when you're outside of this critical juncture, 3/2 times the event horizon, you can do that. But when you start to get to 3/2 times the event horizon, there's no longer any curvature. So it doesn't do any good. You can go as fast as you want to, but it's not going to give you any outward force because you're not traveling in an arc anymore. It gets worse when you go between 3/2 the event horizon and 1 times the event horizon. What happens to the black hole? It doesn't look like a sphere. Now it starts to look like a concavity, and you're falling into it. And so now the curvature of the black hole is actually away from you, and the universe gets compressed into a shrinking circle. And as you go across the event horizon, what do you see? You see that concavity grow infinitely far away and close off and neck off. And at that point, you're gone. I mean, you're no longer in the universe. The universe is now infinitely far away, and you're separated. But what would happen in that case then if you tried to move tangentially? Well, think about this. You're in this big pit. If you try to move tangentially, you're just going to run right into the surface of the black hole, right? So there's nothing you can do at that point. There is no centrifugal acceleration to save you. The only thing you could do is point your engines away from the black hole and try to chug away that way.
If you could find
But
out where the
good luck. Yeah.
black hole even
So the
is.
proposal was that it's far enough away so that, I mean, you're not to the 3.5 times.
And so you're a little further away.
And I don't know what it is, but it was either like a camera or shooting some sort of light, it would magnify it, and it would cause it to heat up a ton if you shot it through the outer layer of the black hole. And then the idea was that you'd have like other holes, and you create this giant light kind of ball, and you could use just the power of.
So like it's like a gravitational slingshot or something.
Yes,
Yeah,
exactly.
okay. I mean, maybe. I don't know. Maybe.
Yeah.
Seems like it'd be pretty hard to engineer, but this is all
You
pretty
could-
speculative.
you
Oh,
You
yeah.
could engineer that though.
Question.
Okay, this is kind of ridiculous. But what if you could build a sphere completely around the black hole, like away from and then it started shrinking in on the black hole? What would happen?
Well, it'd be,
Visually, it looked cool.
yeah. There'd obviously be a point where,
It'd start breaking apart.
yeah, there'd be a
Would it
point
just
where structurally, okay, here's one thing I will say. The bigger the black hole, the better off you'd be.
Yeah.
The bigger the Schwarzschild radius, the further the event horizon is from the center.
Because the rate of
In that
rate of
case,
change of the distance.
is less. And like if it was a small black hole, for example, if you were to dive into the black hole, because your distance from the center is relatively close, just the difference in the gravitational force acting between your feet and your hands would rip you apart, rip you to shreds, right? Pretty quick. It'd be, I mean, spaghettified is what they call it.
Wait, so if you had a big enough one, you could just go all the way in?
Yeah, if you had a big enough one, and you're far enough away from the center, you could dive through the event horizon, and you wouldn't die.
Yeah.
Yeah, yeah.
You can't do it. Is there like a size limit for black holes?
No, no. As far as we know, there is no limit, except the available mass around it. Mm-hmm.
We're going to the lab.
We're going to. Yeah, once you guys grab a seat.